Doing today? I'm good, thank you. All right, so today we are starting our discussion of the respiratory system, which is chapter 22 from your textbook. First, we are looking at the functional anatomy of the respiratory system. The respiratory system starts with the nose, which consists of two major parts forming its skeleton. We have the cartilage of the nose, the nasal cartilage attached to the nasal bone. And inside we've got the cavity of the nose. This is my nasal cavity. Air will be traveling inside the nasal cavity to reach the part of the pharynx located posterior to the nose. If you remember, this is what we've called the nasopharynx. And then air will flow down to pass in the part of the pharynx located behind the oral cavity. We call this is my oropharynx. And then rather than going down to the esophagus, it's going to be moving towards my voice box or my larynx. They are moving down from the larynx to the trachea. This is where it will then be distributed to the two lungs through the right and left main bronchi to reach the lungs. So if we're looking here at the major organs that will share in the formation of my respiratory system, the upper respiratory tract includes the nose, nasal cavity, and we've got spaces inside the facial bones. Those are going to be my paranasal sinuses, and paranasal sinuses will be responsible to enhance the sounds that we emit. Then we're going to be passing through the pharynx. As we've seen here, two parts of the pharynx that the air going to be traveling through, my nasopharynx and my oropharynx. Then down below the pharynx, we're going to be passing through the larynx or the voice box. From the larynx, we're going to be traveling down to the trachea, which is a tube guarded by cartilage rings, hyaline cartilage rings, to keep it patent, to keep it open. Then the trachea conducts the air towards my bronchi and the major branches. And finally, I will reach the air sacs, alveoli, in my lungs. Those again are the major organs sharing in the formation of the respiratory system. Looking closer at the upper respiratory system, this is a 5 stars diagram for the upcoming lab exam. 5 stars diagram. We're looking first at the opening of the nose. This is my nostril. Air will travel. We're going to see at the entrance to the nasal cavity, we have a mucosal depression on here. This is what we call the nasal vestibule. Inside the nasal cavity, if you notice, you can see 3 bony elevations covered with mucous membranes. Those are my nasal meatuses, my nasal conchae, I'm sorry. high nasal concha. So you have a superior nasal concha, middle nasal concha, and inferior nasal concha. In between the nasal concha, you will see tracts where the air going to be traveling. Between the concha here, those are my nasal meatuses. So why it's not smooth inside the nasal cavity? Why do I have elevations and depressions and the air needs to travel between those elevations in the nasal meatus? Simply for the air that you're breathing to become warmer and to add water vapor to it for it to become softer. The air will then reach the part of the pharynx behind the nasal cavity. This is my nasopharynx. And inside the nasopharynx, you can see on the side here, this is the opening of the eustachian tube or the pharyngeotympanic tube. If you remember, when we studied the ears, we mentioned that the ear is formed of three main parts. We have the external ear, which consists of the ear pinna and the external auditory meatus. And at the end of the external auditory meatus, we've seen the tympanic membrane or the eardrum that was responsible to conduct the sound vibrations towards the middle ear, where I keep three tiny bones called my ossicles, malleus, incus, and stapes, for the vibrations to be conducted to my internal ear, where I've got the fluid inside the cochlea. And in the cochlea, you've got the receptors responsible to detect hearing. If you remember, in order for this tympanic membrane to vibrate freely, responding to the sound waves that you are transporting through the external auditory meatus, you need to have equal pressure on both sides of the tympanic membrane. So this middle ear needs to be connected to the atmosphere, to the outside. So for me to have the same exact pressure on both sides of the tympanic membrane. What allows me to be connected to the atmosphere is this canal on here. We call this canal is my eustachian canal or my pharyngeotympanic tube. The pharyngeotympanic tube is going to be connecting the middle ear to the nasopharynx. This is how you would be able to allow the air to flow on the inside of the middle ear, which is a cavity in the temporal bone. And this is going to be needed to equalize the pressure on both sides of the tympanic membrane. Moving down, we can see the oral cavity bounded superiorly by the palate, and you can see here the palate is divided into two major parts. The hard palate, which is the bony part of it was formed by the maxillary bone, and the other part was formed by the palatine bone. And we can see the soft palate, which is a muscular part on here. And as a continuation in the midline of the soft palate, we're gonna have pending down the uvula. So when you open your mouth, what you can see at the end in here, pending down I don't have another diagram for it. Pending down in the midline, at the end of the oral cavity, you've got the uvula. Something also that we need to pay attention to is the presence of tonsils. You can see here in this diagram, three major tonsils. First one on here, this is gonna be my pharyngeal tonsil, which is gonna be located up in the nasopharynx. We've got on the sides of the oropharynx, the palatine tonsil, and in the tongue, we've got the lingual tonsil. So again, three tonsils that we're looking at in here. One is going to be located in the nasopharynx. This is my pharyngeal tonsil. One is going to be located in the oropharynx on both sides. This is going to be the palatine tonsil. And one located in the tongue. This is going to be my lingual tonsil. If we keep moving down, we can see this part of the pharynx is called my laryngopharynx, which is located behind the larynx, or my voice box on here. You see that the voice box is formed of multiple cartilages. The first one and the most superior one on here is called the epiglottis. Epiglottis is going to be responsible to prevent the influx of food and fluids into your airways. So whenever you swallow, you're going to be pulling the larynx up, and the epiglottis kinks down to close your lower air tract. Anteriorly, we have a cartilage on here. This is my thyroid cartilage, and below it we have a smaller one. This is a cricoid cartilage. Inside my voice box, I've got the vocal cords on here. Those are just going to be my vocal fold. Behind the trachea, you're going to see this on here. This is the esophagus. This is the esophagus, where the food going to be going down towards the stomach. And anterior to it, you're going to have the trachea on here. Just in front of the trachea, you've got this butterfly-shaped gland. This is called the thyroid gland. Thyroid gland. Any questions? Any questions? All right, so moving on to the voice production. So how would we be able to produce a voice? The sound has two very important characteristics that we need to be aware of. First is going to be the loudness. And the loudness of a sound is going to be determined according to the amplitude of the sound waves that you are creating. The higher the amplitude of the sound wave, the louder the sound, and the smaller the sound waves that you are creating, the softer the sound. And this is different from the pitch of the sound. The pitch of the sound is going to be determined according to the frequency of the sound waves that I'm producing. So if I am producing faster waves per time, this means I have a high pitch sound. Compared to if I'm producing less vibrations, less sound waves per time, this is going to be a low pitch sound, low frequency. Loudness is going to be determined according to the amount of air and the force of air that you are putting out of your lungs. So when you're speaking, what you're doing is simply pushing air out of your lungs, and this air, as it passes out to the outside of your lungs, it causes the vibration of the vocal cords, and the vibrations here of the vocal cords is what's going to be determining the pitch of the sound. So what determines the loudness of the sound is simply the amount of air that you're pushing out of your lungs, but what determines the pitch of the sound is going to be the frequency of vibration of your vocal cords, which is going to be determined according to the degree of tension that you are applying to your vocal cords. Have you ever seen a guitar before? So How many chords do you have in a guitar? 6. I don't know actually. I believe it was 5. Yeah, 5 or 6. All right, so are all the chords going to be emitting the same exact sound? If you apply the same force on each of them, would they be emitting the same sound? No. Why? Why is it different from one chord to the other? Because each one has a different thickness. And the thickness of the chord is what's going to be determining how fast is this chord going to be vibrating. The faster the vibration, the higher the pitch of a sound. So the thin chords are going to be emitting high-pitched sound. And the thick chords, because they are thicker, so they will have slower vibrations, so they will be emitting a low-pitched sound, a deep sound. All right? So, but in the voice box, we have only 2 chords. We don't have that much variation. So how can we determine the pitch of a sound? Is by stretching the vocal cords. If I want to emit a high-pitched sound, I will be performing more stretch of the vocal cord. If I want to emit a low-pitched sound, I will need to relax my vocal cords so that I will have less vibrations. It's like when you have a rubber band and you pull it and you vibrate it. It's going to be vibrating much faster if you don't, compared to if you don't apply tension to it. So the more tension that you apply before you vibrate this rubber band, the faster it vibrates and the higher the pitch of sound it emits. This is the same exact concept when we look at the pitch of the sound emitted by the vocal cords. So again, how would I determine the pitch of a sound emitted by the vocal cords? It's going to be simply by changing the degree of tension of the vocal cords by either relaxing the vocal cord or stretching the vocal cords. This sound that we have emitted from the larynx by vibrating the vocal cords needs to be modified, and the modification of the sound here is going to be taking place in the pharynx, in the oral nasal cavities, and the nasal sinuses. And all those cavities together will be amplifying and enhancing the sound. One last thing that we need to do, other than enhancing the sound, it's going to be shaping those sounds into a language. And in order for me to shape the sound into a language, I need to have a coordinated muscular movement. So, for example, if I'm saying O, I need to purse my lips. Can you say O without pursing your lips? Will it sound O? Can you say O when you are, while you are smiling, for example? It won't sound O, right? So in order for me to shape the sounds into a language, I need to have many muscles to contract and relax. And this includes the muscles of the tongue, the muscles of the pharynx, the soft palate, your lips. I have a huge number of muscles that need to coordinate together in order to modify those sounds into a language. Any questions? Any questions on how do we produce a voice production? All right, so moving on to another important diagram. This is a diagram showing the vocal cords on here. If you notice, the vocal cords are actually formed of connective tissue bands. Those white parts, those are the ones which will be vibrating. Those are what we call the vocal fold or the true vocal cords. But on both sides of the true vocal cords, I have muscular vocal cords. We call those are my vestibular folds or my folds vocal cords. So why do I call them folds vocal cords? Because simply they are not emitting any sound. They are just determining the degree of stretch of the vocal cord, of the true vocal cords. So those are here the true vocal cords. Those are the false vocal cords or my vestibular folds. You see on here, this is the base of the tongue. And just behind the tongue and above the voice box, you're going to have this cartilage that will be preventing the passage of the food down to your airways. This is your epiglottis. You can see the cuneiform and corniculate cartilages building up parts of the wall of my voice box. When I'm emitting the sounds, the vocal cords are going to be semi-closed. So they are not fully relaxed. They are not fully closed. They are in between. So for those vocal cords to vibrate in response to the air moving out from my lungs. So when I open my vocal cords, as you see on here, when I open the glottis, I can see those rings of the trach. Moving on to the respiratory zones. First zone is my conducting zone, and the conducting zone is not going to be performing any gas exchange. No gas exchange will be taking place in this zone. This includes my trachea and the bronchi, which are branches of the trachea, all the way until I reach my terminal bronchioles. The respiratory zone, this is going to be the site for gas exchange, and it consists of microscopic structures. Those are what we call the respiratory bronchioles, the alveolar ducts, and the alveoli. All right, so the first question today, which of the following allows gas exchange? Alveoli, alveolar ducts, respiratory bronchioles, and all of the above. Which one do you think? Which one allows gas exchange to take place? All of the above, exactly. All of the above. The most common wrong answers that I see on the exam is alveoli. Yes, alveoli gonna be performing most of the gas exchange, but all of the three are part of the respiratory zone, and all of the three will allow gas exchange to take place. But gas exchange mainly takes place in the alveoli, but all of them gonna be allowing it to take place. Other than the conducting zone and the respiratory zone, we've got the respiratory muscles, and this includes the diaphragm and other muscles that will allow the ventilation, like my intercostal muscles, external and internal intercostal muscles. Abdominal muscles also gonna aid in forced expiration. So in order to allow the ventilation to take place, as we're gonna be studying, we're going to be in need of multiple respiratory muscles. The most prominent respiratory muscles that we've got, it's going to be the diaphragm. Moving on to the conducting zone, we start from the trachea. Trachea going to be dividing into two main bronchi. I have the right main bronchus and the left main bronchus, which enters the lung at the hilum of the lung in here. Each main bronchus gonna split into lobar bronchi. Each main bronchus gonna split into lobar bronchi. We've got three lobes in the right lung, and we've got two lobes in the left lung. Each lobar bronchus gonna split into smaller branches. Those are my segmental bronchi. Other names: primary bronchus, primary bronchi, same as main bronchi. Lobar bronchi are also called the secondary bronchi, and the segmental bronchi are also called the tertiary bronchi. Tertiary bronchi. We're gonna end up having 23 orders of branching. So 23 times we're gonna have divisions throughout the pulmonary tree. I will reach the bronchioles, which are less than 1 millimeter in diameter, which will conduct to the terminal bronchioles, which are the smallest. So again, started by having trachea. Trachea here splits into two main bronchi. Each main bronchus splits into lobar bronchi, and each lobar bronchus is gonna split into segmental bronchi. And I will keep branching 23 times until I reach my terminal bronchioles, where I will be connected to the respiratory zone. Our second question for today: once inspired air enters the nasal cavities, the next area in the upper respiratory tract it comes in contact with, it's going to be which of the following here? Larynx, laryngopharynx, nasopharynx, oropharynx. What is the area that once the air flows out into the nose, it gets in contact with after it passes the nasal cavity? What do you think? C, nasopharynx, nasopharynx. Yes, exactly, nasopharynx. If you see back at Looking back at this diagram, you see the first part that you get in contact with, located behind the nasal cavity, it's the nasopharynx. Nasopharynx. Moving on to the respiratory zone. Again, the respiratory zone includes the respiratory bronchioles, alveolar ducts, and the alveolar sacs. Alveolar sacs, those are, as you see, clusters of alveoli. So all this together, it's an alveolar sac. Each one of them is going to be an alveolus. We have around 300 million alveoli that will account for most of the lungs volume. And again, the alveoli, those are going to be the main site for gas exchange. Those are going to be the main site for gas exchange. Again, where gas exchange takes place, it's going to be taking place in all the three of them, all the three: respiratory bronchioles, alveolar ducts, and alveolar sacs. But again, main site for the gas exchange, it's going to be the alveoli. All right, so here somebody is asking about the previous question, right? All right, so again, the previous question was asking about where the air goes after it moves from the nasal cavity. So the first site that I get in after I move through the nasal cavity is going to be the nasopharynx. Nasopharynx. All right, so we see on here, this is going to be the cluster of alveoli, my air sacs. You see blood is coming in, getting low oxygen levels. Once it gets in contact with the air sacs, you're going to have the gas exchange taking place, and the blood that will be drained out from the lungs, it's going to be carrying much higher levels of oxygen. So here I'm getting blood at low oxygen levels, and the blood that gets drained out carries high oxygen levels. So which one is a vein, which one is an artery? So this is number 3 for the in-class activity for today, and this is number 4. And you've got 2 choices on here. A, artery, and B, vein. Which one would you say it's an artery? Which one would you say it's a vein? Three is a vein, right? 3 vein, 3 vein. 4 artery. So the answers that I've got here, 3 vein. Number 3 is marking a vein, and number 4 is marking an artery, right? Anybody disagree? Anybody disagree? Anybody disagree with this? Yeah, we've got 1 disagreement. 2. Anybody Disagrees? 3, yes, exactly. So actually, no, here. Number 3 is the artery. Why? Because remember, an artery is carrying the blood away from the heart. So it carries the blood to the lungs. So those are the pulmonary arteries. This is my artery. And the ones that will be draining the oxygenated blood back to the heart to reach the left atrium, it's going to be the pulmonary veins. All right, so you see on here, veins are red colored because this is a pulmonary vein. And the artery here, it's blue because it carries low oxygen. All right, so it's gonna be an artery. So again, number three is the artery. It carries deoxygenated blood. And number 4 is my vein, as it carries oxygenated blood back to the heart. So vein means you're going back to the heart, and artery means you're carrying the blood away from the heart. Right? It doesn't matter what's the state of oxygenation of the blood. What matters is the direction of the blood flow. All right, does this make sense? Does this make sense? Questions? All right, looking closer at the air sacs, we can see 2 types of alveolar cells. We have type 1 alveolar cells, as those are the ones responsible for the gas exchange to take place, for the carbon dioxide to leave the air sacs to be carried by the red blood cells, and for the carbon dioxide to leave the blood and to be conducted to the air sacs. All right, so this is type 1 alveolar cells. Those are the cells responsible again for the gas exchange. The second type of alveolar cells, or type 2 alveolar cells, those are the cells responsible to release the surfactant. What is the surfactant, and why do I need it in my lungs? So let's look back at some chemistry, the chemistry of the water. If you remember, oxygen has how many electrons as an atom? You remember the atomic number of oxygen? What is the atomic number of oxygen? Uh, less 8, exactly 8. So if you remember, the first energy level has 2 electrons, becomes saturated having 2 electrons. Next is going to be C16 is the atomic mass. Atomic number is the number of protons, just protons. So we've got 8. So the next energy level, or the valence shell, is going to have the remaining 6 electrons. So in order for me to become chemically stable as oxygen, I need to get 2 more electrons for my outer energy level to become saturated, to contain 8 electrons. So remember when we discussed the covalent bonds, the hydrogen has 1 proton and 1 electron. So it still needs 1 electron to become chemically stable. I'm formed of 1 proton and 1 electron. So this oxygen will have an agreement with those 2 hydrogens for him to share 2 of his electrons with each one of his electrons with each one of them. So in the chemical bond where I will be sharing electrons, this is what we call the covalent bond. So the attachment between the oxygen and the 2 hydrogens, it's a simple covalent bond where the oxygen is sharing 1 pair of electrons with each of the 2 hydrogens. This is how the water molecule gonna look like. The atomic mass for oxygen is 16, but the atomic mass for the hydrogen is just 1 because I have only 1 proton in my nucleus as hydrogen. Compared to the oxygen, it has 8 protons, 8 neutrons, so it has a much greater atomic mass. So what happens when I have this difference in the atomic mass between the oxygen and the hydrogen? Remember, having a higher mass gonna be pulling the electrons towards it. So the electrons, yes, they are shared. They were not lost by any of the atoms. But those electrons are going to be pulled towards the oxygen for most of the time, simply because the oxygen has a much greater mass. So what happens when I pull the electrons towards the oxygen side of the water molecule becomes more negatively charged, and the hydrogen side of the water molecule becomes more positively charged. So if we're looking here at water, this side is more negatively charged, and this side is going to be more positively charged. And another water on here. The hydrogen side is more positively charged, and the oxygen side is going to be more negatively charged. So what happens between this hydrogen and the oxygen of another water molecule, between a side which is more positively charged and the side which is more negatively charged? Will I have attraction or repulsion between the two? Between the hydrogen of one water molecule and the oxygen of another water molecule? Will they have attraction or repulsion? Attraction, right? And this attractional force that we've created between the water molecules is what we've called the hydrogen bond. Hydrogen bonds are going to be so strong while you are in direct contact with air. And this is what creates the surface tension of the water. If you remember, inside your lungs, you have we have 300 million alveoli that are forming most of the lungs volume. So can you imagine how small is the alveolus? In order for me to allow the gas exchange, I need to have a film of water lining those tiny alveoli for the soluble gases to move in and out of my alveolus. So if we're looking here It's a very tiny space. I have water lining the alveoli. So why I want have a tractional force between the water molecules lining the inside of my alveoli, collapsing my lungs. Actually, there is a very strong attractional force between the water molecules lining those air sacs, but I have something that will be reducing the surface tension here, preventing my lungs from collapsing, and this is what we call the surfactant. The surfactant, it's gonna be released from the type 2 alveolar cells. Surfactant is a detergent-like lipoprotein that will be reducing the surface tension of the water, preventing your lungs from collapsing. So if you have a cup of water and you put oil in the water, would you be able to mix the water with the oil? What do you think? Would you be able to mix the water with oil? No. Remember, what prevents the oil from being mixed with water is the water surface tension. So the oil will float on top of the water and it won't be mixed with it. So looking on here, add this detergent. So you add a detergent. What the detergent will do, it's going to be reducing the surface tension between the water molecules, allowing you to mix the oil with the water to make the fat more water solid. This is the same exact concept of the surfactant. Surfactant is a detergent-like lipoprotein that will reduce the surface tension created by the water molecules inside the alveoli. A 5 stars diagram on here. This is going to be the diagram showing the transverse section of the thoracic cavity, showing the lungs surrounded by this double layered serous membrane. This is my pleura. Showing the hilum of the lungs. This is where the pulmonary artery and vein gonna enter and exit, and the main bronchi as well. Between the lungs, we've got the heart surrounded by the pericardium, and the major arteries and veins going in and out from the heart. Located posterior to the heart, we've got the lower part of the esophagus, as you see on here. All right, so how do we breathe? How air flows from outside to the inside of the lungs and from inside out by inspiration and expiration. So let's imagine this is my lung on here. This is the trachea. This is my lungs. Just for simplification. A very important concept that we need to be aware of in order to understand the mechanics of breathing is the relationship between the volume and pressure. And here, what I mean by the volume is the volume of the container, not the content, the container size. What happens to the pressure inside the container if I increase the volume of the container? What do you think? pressure decreases. So try to imagine you are 5 people in the family, and this is your home. Then you moved to a larger home. Would you have more or less pressure applied on you? Less pressure. So when I increase the volume, what happens to the pressure of the particles inside this container? I will have a decrease in the pressure applied on the particles. So again, when I increase volume, pressure inside drops. When I reduce the volume, the pressure increases. This is very, very important concept. Another very important concept is that anything flows from high pressure to the side with lower pressure. So whenever I have high pressure of blood, blood will flow from high pressure to the side with lower pressure. If I have high pressure of air, air will flow from high pressure of air to low pressure of air. So again, anything going to be traveling from high pressure to low pressure until when? Until I equalize the pressure on both sides. So air here flows from high pressure to low pressure until I equalize the pressure on both sides. So looking here at the thoracic cavity, you'll see those are my ribs on here of the chest cavity. And this would be my diaphragm, covering the lungs from outside and lining the thoracic cage. You're going to have a double membrane, double layers membrane. This is called the pleura. So I have an outer layer of the pleura. This is my parietal, and I got the visceral layer of the pleura covering the lungs tissue. What happens during inspiration? During inspiration, the diaphragm is going to be contracting and it's going to be moving down like this. Diaphragm moves down. So what happens to the volume of my thoracic cavity? If I have a depression in the diaphragm did move down, what happened to the thoracic cavity volume? What do you think? What happens to the volume of your thoracic cavity when you depress the diaphragm like this? What happens to the volume? The volume increases, right? So what happens to the pressure within the chest cavity? If I increase volume, what happens to the pressure? I will have a drop in the pressure. And what is the pressure inside the thoracic cavity? It's my intrapleural pressure. If you remember, the space between the visceral layer and the parietal layer of the pleura is going to be creating a vacuum. So I have a vacuum on here. I have a negative pressure between the two layers. If you remember from the cardiac chapter, why do I have a negative pressure between the two layers of the pleura? Remember, your lungs have tendency to collapse and your chest wall has tendency to expand. So when you are pulling the two layers away from one another, what's going to happen? You are creating a vacuum. You're creating a negative pressure. What I mean by a negative pressure, it's a pressure lower than my atmospheric pressure. What is atmospheric pressure? It is the pressure of the atmosphere. The pressure of gases that will be surrounding you from your surface, from whatever surface, all the way until you reach the space. All this is going to be considered your atmospheric pressure. Atmospheric pressure, it's going to be 760 millimeter mercury, but we're going to be considering 760 millimeter mercury as our zero pressure. So if, for example, the intrapleural pressure is 756, so it is lower than the atmospheric pressure. So I won't keep saying 756, I will just say it's -4 millimeter mercury, because I've considered the atmospheric pressure to be my zero pressure, because it's applied on anything on Earth. Atmospheric pressure is my zero pressure. And the intrapleural pressure is always a negative pressure, because the lungs have tendency to collapse and the chest wall has tendency to expand. So the pressure in between, it's always going to be a suction pressure. And this is what keeps your lungs inflated. This suction pressure applied on the outside of your lungs is what keeps your lungs inflated. Without this suction force on the outside of the lungs, my lungs would collapse. So let's check this example on here. If I have a balloon and I want to inflate this balloon, how can I inflate this balloon? I want two different ways to inflate this balloon. What do you think? You can directly pump air inside, or you can create a suction force from outside of the balloon, and this suction force is going to increase the volume of the balloon, so this creates a negative pressure pulling air in. So was this what we're doing with the lungs? We are actually creating a vacuum around the lungs to pull the air to the inside of the lungs. So the difference between the pressure inside the lung and the pressure outside the lung, this is the effective pressure that's going to be determining the volume of my lung. If I don't have negative pressure outside, if I don't have a negative pressure outside, no air will flow inside the lungs. If I don't have this positive pressure going in to my lungs, I wouldn't have been able to inflate the lungs. So simply speaking, if I have a balloon, in order for me to know how big would this balloon get, I need to calculate the difference between the pressure inside this balloon and the pressure outside this balloon. And I will check the difference between the two. So if let's say I have a zero pressure inside and zero pressure outside. Would there be any inflation? Would there be any increase in the size of this balloon? What do you think? Inside pressure is a zero pressure. Outside pressure, compressing pressure, is a zero pressure. Would there be any change in the size of this balloon? What do you think? No. How about if I have a pressure of 10 millimeter mercury, air coming in by a pressure of 10 millimeter mercury inside, but I'm compressing this balloon from outside by another pressure, which is also is 10 millimeter mercury. Would I have any inflation of this balloon? No. Why? Because the pressure pushing the wall of the balloon out is equal to the pressure applied on the outside of this balloon. So there will be no increase in the size. There will be no inflation of the balloon. So let's see another example on here. This is my balloon, and I'm compressing this balloon by a pressure of 5 millimeter mercury, but I am pushing from inside of the balloon by a pressure of 10 millimeter mercury. Would there be any inflation of this balloon? In this case, I'm blowing air in at 10 millimeter mercury, and I'm compressing the balloon from outside by a pressure of 5 millimeter mercury. Would there be any inflation? Yes. What is the effective pressure by which this balloon going to be inflated? What do you think? What is the effective pressure that's going to be inflating this balloon? The difference between the pressure inside and the pressure outside. So the effective pressure is 10 minus 5. It's going to be 5 millimeter mercury. So this balloon is going to be inflated by an effective pressure of 5 millimeter mercury. Let's see another example on here. This is my balloon on here. I'm not pumping air in. I'm not creating a positive force inside or a negative force inside this balloon. But I am creating a suction force outside of this balloon of 5 millimeter mercury. So inside is 0. Outside, I am negative 5. It's a suction force. So what's going to be the effective pressure that allows this balloon to be inflated? Will it be inflated first? Yes or no? Will this balloon be inflated? Yes. What is the effective pressure that will allow it to be inflated? What do you think? What is the effective pressure that allows this balloon to be inflated? Pressure inside minus the pressure outside. So 0 minus negative 5 is equal to 5. The difference between pressure inside and pressure outside is what creates the net effective pressure that's going to be determining how big this balloon will be. Is this concept clear? So the effective pressure that determines whether this balloon is going to be inflating or deflating, it's going to be the difference between the pressure inside and the pressure outside. So again, back to the lungs. Looking here at the lungs, we've seen two pressures. We've seen the atmospheric pressure, which is 760 millimeter mercury, but we're going to consider it as a zero pressure. And we have the pressure inside the thoracic cavity, intrapleural pressure, which is -4 millimeter mercury. Inside the lungs, I have a pulmonary pressure. And as you see here, the lungs are directly connected to the atmosphere. So air will be always moving in and out to do what? To equalize the pressure on both sides. So the pulmonary pressure is almost always a zero pressure. It's almost always equal to the atmospheric pressure. Again, why? Because the lung air sacs are directly connected to the atmosphere. So whenever I have an increase in the pressure inside my lungs, the air flows out. Whenever I have a decrease of the pressure inside my lungs, air will flow in. So always air gonna be flowing in and out for the pressure to be equal to the atmospheric pressure. I have a direct path of the air to equalize the pressure on both sides. So what is the pressure outside of the lungs? It's my intrapleural pressure, which is -4 millimeter mercury. It's lower than the atmospheric pressure by 4 millimeter mercury. The pressure inside my lungs, it's equal to the atmospheric pressure. This is my pulmonary pressure. It's equal to the atmospheric pressure, so it has a pressure of 0 millimeter mercury. So let's have a look on here on how air flows to the inside of the lungs during inspiration. This is again my lung. This is my thoracic cage. And this is my diaphragm. Remember the serous membrane formed of two layers covering the lungs and lining the thoracic cavity. This is my pleural. So again, the pressure here, it's my intrapleural pressure. It's -4 millimeter mercury. The pressure in the atmosphere, atmospheric pressure, it's 0 millimeter mercury. And what keeps my lungs inflated is the difference between the pressure inside the lungs and the pressure outside the lungs. So what is the pressure that keeps the lungs inflated? If this is a zero pressure, 0 millimeter mercury inside the lungs, and outside the lungs, I have a -4 millimeter mercury. What is the effective pressure that keeps my lungs inflated? Remember, how do we calculate the effective pressure that keeps this balloon inflated? We check pressure inside minus the pressure outside. So what is the effective pressure in this case? It's a 0 minus -4 millimeter mercury. The effective pressure that keeps my lungs inflated, it's equal to 4 millimeter mercury. We call this pressure, it's my transpulmonary pressure. This is the effective pressure that keeps your lungs inflated. All right, so what happens during inspiration? During inspiration is an active process during which you're going to be contracting the respiratory muscle, most importantly, the diaphragm. So when I contract the diaphragm is going to be moving down. And as you see, what happens to the thoracic cavity volume as I pull the diaphragm down, the volume here of the thoracic cavity, it's going to be increasing. So I have an increase in my volume when I contract the diaphragm. And if I increase the volume, what happens to the pressure? Can you remind me? When I increase volume, what happens to the pressure? Would I have higher pressure or lower pressure? Increase or decrease? Increase volume, gonna result in what again? Increase in the volume, gonna result in a decrease in the pressure. So here in the thoracic cavity, I've got a pressure of 0 millimeter. In the thoracic cavity, I have a pressure of -4 millimeter mercury, which is the intrapleural pressure. So when I increase the volume, this pressure is going to be decreasing. So when it decreases, what's going to be the intrapleural pressure? Let's say I did decrease the intrapleural pressure by 1 millimeter mercury. What's going to be the intrapleural pressure now after I increase the volume of the thoracic cavity, contracting the diaphragm? -4. If it decreased by 1 millimeter mercury, what's going to be the current intrapleural pressure? Any idea? My intrapleural pressure is -4. It decreases by 1 millimeter mercury. So what's gonna be the intrapleural pressure after I contract the diaphragm? It's gonna become -5 millimeter mercury. So if my intrapleural pressure becomes the -5 millimeter mercury, so what's gonna be the change in the transpulmonary pressure as a result? So when I contract the diaphragm, you see transpulmonary pressure, rather than being 4, is going to become 5 millimeter mercury. And can you remind me what is the transpulmonary pressure by definition? Transpulmonary pressure, it's the effective pressure that keeps my lungs inflated. So what happens when I contract the diaphragm? The effective pressure that keeps my lungs inflated gonna increase. So rather than having an effective pressure of 4 that keeps my lungs inflated, the effective pressure now goes up to 5. So what happens to my lungs volume as a result? Lungs volume gonna increase. And when I increase the lungs volume, what's gonna happen to the pressure inside the lungs? The pulmonary pressure or intra-alveolar pressure. If I increase the lungs volume, what's gonna happen to the pressure inside the lungs? It's gonna decrease. So rather than 0 pressure, it becomes -1 millimeter mercury. And what is the pressure outside of the lungs that I'm connected to? It's my atmospheric pressure, which is equal to 0 millimeter mercury. So which one is greater, 0 millimeter mercury or -1 millimeter mercury? Which one is higher? 0 is higher. So air will flow from the atmosphere to the inside of your lungs, equalizing the pressure. So this -1, after the air flows in, it returns back to 0 after I allow the air to move into my lungs. This is how inspiration takes place. How about expiration? So the exact opposite. See, at the end of inspiration, what is the intra-alveolar pressure, or the pulmonary pressure, is equal to, the pulmonary pressure is equal to 0 because I did allow air in. And the transpulmonary pressure that keeps my lungs inflated is 5 millimeter mercury, because the intrapleural pressure is -5 millimeter mercury. This is when at the end of inspiration. During expiration, what's going to happen? The exact opposite. So let me draw this in a different color here. So we'll be drawing in yellow here for the expiration. So during expiration, it's a passive process. I don't need to contract muscles normally for expiration, for normal expiration. What I will need is just to relax the respiratory muscles. So when I relax the diaphragm, what's going to happen? The diaphragm is going to be moving up, and as a result, what's going to happen to my thoracic volume? Thoracic cavity volume. What's going to happen to the volume of the thoracic cavity? When the diaphragm moves up, I will have a reduction in the volume of the chest. And when I reduce the volume of the chest, remember, when I reduce volume, what happens to the pressure? When I reduce the volume, what happens to the pressure? Pressure increases. So the intrapleural pressure, rather than being -5, it becomes -4 another time. It did increase by 1 millimeter mercury. So intrapleural pressure now, as I relax the diaphragm, it becomes -4 millimeter mercury. So the transpulmonary pressure, rather than being 5, it returns back to become 4. So the effective pressure that keeps my lungs inflated, it was at the end of inspiration 5 millimeter mercury. This is the effective pressure that keeps my lungs inflated. I did decrease this pressure. So the effective pressure that keeps the lungs inflated, transpulmonary pressure, it's reduced. So what happens to the volume of the lungs? If I have a reduction in the effective pressure that keeps the lungs inflated, the volume of the lungs will be decreasing. And remember, when you decrease the volume, what happens to the pressure inside? When I decrease volume, pressure inside increases. So rather than having a 0 millimeter mercury, I will have 1 millimeter mercury of air pressure. So which one is greater? 1 millimeter mercury in your lungs or 0 millimeter mercury in the atmosphere? Which one is greater? 1 millimeter mercury in the lungs. So air will start to flow from high pressure within your lungs to low pressure in the atmosphere. Air is going to be leaving the lungs, moving out. This is how expiration going to be taking place. So again, what allows inspiration and expiration to take place? Remember, during inspiration, the inspiratory muscles will contract. So the diaphragm is going to be moving down, rib cage is going to be moving up. This would increase the volume of the thoracic cavity. As I increase the volume of the thoracic cavity, the intrapleural pressure gonna be decreasing. And as intrapleural pressure decreases, the transpulmonary pressure gonna be increasing. And as the transpulmonary pressure increases, the lungs will be stretched. And as you stretch the lungs, what's gonna happen to the pressure inside your lungs? The intrapulmonary pressure will drop. Rather than being a zero pressure equal to the atmospheric pressure, it becomes a negative pressure. It's gonna become a negative 1 millimeter mercury. So outside of the lungs, I have 0 millimeter mercury. Inside my lungs, I have a negative 1 millimeter mercury. So air will flow from outside to the inside, from high pressure to low pressure. As the air flows to the inside, where you're gonna have lower pressure, it's gonna be equalizing the pressure on both sides. So the air pressure inside the lungs will increase back to be equal to the atmospheric pressure. It increases to a zero pressure. What happens during expiration? Remember, expiration, it's gonna be a passive process. What I will need to do is relaxation of the inspiratory muscles. I relax the diaphragm is gonna be moving back up to its place. I relax my intercostal muscles, so I will have drop in my rib cage, and all this together are going to be reducing the volume of my thoracic cavity. Reduction in the volume of the thoracic cavity gonna increase the intrapleural pressure. So rather than being -5, it increases to become -4 another time. This reduction in this increase in the intrapleural pressure gonna result in a reduction in the transpulmonary pressure, the effective pressure that keeps my lungs inflated. So if the effective pressure that keeps my lungs inflated drops, what happens? The lungs will recoil passively. And when it recoils passively, what's going to happen? When I decrease the volume of the lungs, the pressure inside the lungs gonna rise. So rather than being 0 millimeter mercury at the end of an inspiration, now it becomes 1 millimeter mercury. So now inside the lungs, I have higher pressure compared to the atmospheric pressure. Inside the lungs, I have 1 millimeter mercury. Outside in the atmosphere, I have a 0 millimeter mercury. So what's going to happen? Air flows from high pressure within my lungs to low pressure in the atmosphere. Air leaves. So the gases here will flow out of the lungs down its pressure gradient until the pulmonary pressure returns back to a zero pressure. That's why we said that the pulmonary pressure or intra-alveolar pressure, it's almost always equal to zero. Almost always, excuse me, almost always equal to the atmospheric pressure. Questions? All right, so for question number 5 for today's in-class activity, what do you think? The functional unit of the lung is found in what part of the lower respiratory system? Conducting zone, bronchial zone, respiratory zone. In which of those zones on here I can find the functional unit of the lungs? bronchial zone. Any other ideas? 2, bronchial zone. What is the functional unit of the lungs? What is the functional unit of the lungs? The part that performs most of the gas exchange. What is the part of the lungs that performs most of the gas exchange? What do you think? It's my alveoli. And remember, the air sacs and alveoli are part of which zone? Did we mention something called the bronchial zone? We mentioned 2 zones, right? Conducting zone and respiratory zone. So where can I find? Where can I find the functional unit of the lung? Conducting zone, bronchial zone, or respiratory zone? I'm waiting for some responses here. Respiratory zone. Respiratory zone. Questions? All right, we can have a break for 10. We'll come back, discuss more about the respiratory system.